Hello, everyone. It is Friday, TGIF. I had a really great week, and I hope you all had a great week as well. So in this video, I wanted to give an example of something you might encounter in Calculus 3. So if I'm not mistaken, this is my first Calc 3 video I've ever made. So Calc 3 is the branch of calculus that takes everything we've learned in Calc 1 and Calc 2 and applies it into multiple dimensions. So for example, we have a derivative which tells us the rate of change of a function at a particular point. It tells us how fast a function is changing, the instantaneous rate of change at that point. We could actually apply that same principle to 3 dimensions. So what if we didn't have just a curve? What if we had a surface? So a surface is what you get when you have 3 dimensions and you have a function of more than one variable to give you the height of a curve at a particular point, a height of a surface, I should say, at a particular point. So instead of y depending on x, we have a new variable z, which depends not only on x, but also on y. So I'm not even going to draw, I'm going to try to draw a surface, but it's not going to be pretty. So imagine a blanket that's covering your Cartesian plane, and it's lumpier in some areas than it is in others. And the measure of how high it goes depends on your point. So this point has an x and it has a y. The height of the point is a function that depends on x and on y. And then you can actually figure out the rate of change at that point. It's not just going to be the rate of change of, it's not going to be a tangent line, it's actually going to be a tangent plane. So we can actually kind of draw a tangent plane to show the rate of change of this point on this surface. Pretty crazy stuff. And then something else we can do in 3 dimensions is multiple integration. So we know at this point that an integral tells us the area under a curve. So if this is our generic looking function, the integral from a to b tells us how much area is between the curve and the x-axis. So imagine that instead of having it be just a dx integration, here, let me erase this part we don't need anymore. So to reiterate, we know I'm going to use lowercase a for area. We know that the area under the curve is the definite integral from a to b of this generic function that I just drew, f of x dx. So this is a dx integration because we're dealing with a change so small that it's infinitesimal. Each rectangle width is getting smaller and smaller and smaller until it's as close as it can get to 0 without actually being 0. So we are integrating in 1 dimension. We're integrating in the x dimension only. So what if we wanted to have a volume and not just an area? So we know area is flat. It's 2-dimensional. Volume is not flat. It has 3 dimensions. So what if we wanted to extend this to make it a volume and we didn't want to make it circular? So we know that by this point we use the shell method, the disk method, the washer method, and the known cross sections method to give us these circular volumes. But what if you wanted something that's not so circular? What if you wanted something a bit more rectangular? In this case, you would do multiple integration. So instead of just having an x and a y axis, we're also going to include a z-axis this time. Pretty exciting stuff. So that's our z-axis. And imagine we are taking our area and we are extending it this way so that we no longer just have a flat 2-dimensional figure. We've made it into a 3D shape. And it looks like this somewhat. So that begs the question, how do we even get the volume of this? We know how to get the area of a 2D figure, but what about the volume of a 3D solid using this convention right here? So this is where we have to use multiple integration. So not only are we going to have a dx integration from a to b, we are going to have a dz integration because we're going to be integrating now along the z-axis. We're going to be going from b, I'm going to call this c right here. So a multiple integral looks like this. Area is going to be one integral and then two integrals. And then whatever our function happens to be. So you could have a function of f, you could have a function f of x, and then you can integrate that along the dx scale and then along the dz scale. And then we know that for the dx integration, we're going from a to b. And then for the dz integration, we're going from b to c. So that is how that part works. So the way we approach something like this is the dz, the first differential only applies to the first integral. So we're integrating from a to b only for the dx integral. And then once that's taken care of, we're going to be integrating from b to c for the dz integral. So it really does matter a lot the order you put the differentials in. They have to match the integral that you want it to be part of. All right. So now let's move on to a more concrete example. So from geometry, we know that the volume of a sphere is given by 4/3 pi r cubed, where r is the radius of our sphere. And if you're like me, you might have been wondering where this came from. How is that possible? Like, how do we even know what the volume of the sphere could be this? And the answer might shock you. So we know that our sphere is going to look like this. We have the center of the sphere right there. And then because it's a volume problem, we're going to have three axes. We have, this is going to be our z-axis, and then our x-axis, and then our y-axis. So we have multiple axes to consider because a sphere is a 3D figure. So how do we get this volume? Where does the 4/3 pi r cubed come from? It came from a multiple integration situation. So in the last example, we had two different integrations we were doing. We had a dx integration for the length, and then a dz integration for the width. That got us a volume. But consider that that only works if you're dealing with rectangular coordinates. Rectangular coordinates are an x and a y and a z. Conveniently enough, volume is just x times y times z, length times width times height. But this thing we have right here doesn't exactly play by those rules. That's the problem. So we're going to be dealing with an alternate coordinate system. We're not going to be dealing with rectangular coordinates or Cartesian coordinates. We're going to be dealing with something called spherical coordinates, where instead of an x and a y and a z, we have a radius. This is the radius of our sphere. We usually just use r to refer to the radius, but in this situation, we're going to call it rho. This slanted looking p, it's a Greek letter called rho. And in vector calculus, that just tends to be the most common letter identifier we use to notate a radius. So that's our radius. That's one of the variables we have in circular coordinates, spherical coordinates, I should say. And then another one we have is an angle. So it's the angle going from here to there. So we're going to call this angle phi. And then we have one more angle. So it's going to be the angle going from here all the way through, and we're going to call this theta. So we have a rho, we have a phi, and we have a theta. So the area of the sphere, or sorry, the volume of the sphere came from this triple integral. So we have an integral for rho, and for phi, and for theta. And the function we integrated to get the volume of the sphere is rho squared times sine of our angle phi. And then again, it's really important the order you put the differentials in. Otherwise, it just doesn't make a whole lot of sense. So we're going to do the d rho integration first, and then the d phi, and then the d theta. And the limits of integration for phi, well, we want to leave the radius just as the radius. So if we had a set radius, Like if we had a radius of 1, for instance, we would make this 0 and then 1. So this would be for a radius of 1. This, for example, would be for a radius of 2. But I want to leave the radius as a variable because the radius could be anything. So instead of going from 0 to a number, I'm going to go from 0 to r for radius. And now we have phi. So the angle phi, it looks like we're starting at 0, and then we're going halfway through the unit circle, landing on pi. So the limits of integration for phi should be 0 to pi. And then for theta, we know we're starting at 0, and then we're doing 1 full revolution through the circle. So we know 1 full circle would be 2 pi. And as far as where this part came from, this is really hard to explain without linear algebra. This actually comes from something called the determinant of a Jacobian matrix. So remember that a matrix can have a set number of elements. I'm going to skip some. Suppose this is our 3x3 matrix. And remember, there are ways of figuring out the determinant. And the determinant gives us a lot of useful information about a matrix, including the values that will give us eigenvalues to solve the characteristic equation. So the determinant is highly useful. And the determinant of a Jacobian matrix is where this part here comes from. And maybe in a later video, I'll cover that in a little bit more detail, maybe some more detailed linear algebra videos to show exactly where this came from. But for the purposes of this video, we're not going to get into that. I'm not going to get into where that integrand came from. All right. So let's do some multiple integration. So like I said before, we start from the inner layer and work our way out. So we're going to be dealing with the d rho integration first. So what I like to do is I like to color code things. Maybe I'm weird, but some of my students said it's been helpful for them too. So we have a rho here, and this is our differential with respect to rho. And then this sign right here, this involves phi, and then we have d phi right there. So that means for the first integration, it's a d rho integration. We're going to ignore this part. We're going to ignore the sign of phi and just deal with that a little bit later. So we're going to take the antiderivative of rho squared. So that's going to get us 1/3 rho to the 3rd power. Integral 0 to 2 pi. Integral 0 to pi. And then, like I said, we have 1/3 rho to the 3rd power. And we're integrating from 0 to r. And then we have sine of phi. And then we already dealt with the rho, so the d rho goes away. We don't have that differential anymore. We have just d phi and d theta left to deal with. So let's deal with this part right here. So if we plug in r, we get r cubed. If we plug in 0, we get 0. So that means everything in here works out to be 1/3 rho cubed minus 0. So just 1/3 rho cubed. And because we already dealt with that part, we can actually just move it outside the entire integral. So I'm going to move 1/3. This is going to be 1/3 r cubed. We're going to replace the rho with an r. So this is going to be 1/3 r cubed, 1/3 r to the 3rd. And then we want to take the antiderivative of sine of phi. So we know that the antiderivative of sine is negative cosine. So this is going to be negative. I'm going to put the negative out front of everything to simplify things a little bit. So we have the negative. And then we already took the integral of the phi, the sine of phi. So we only have one integral left. The integral from 0 to 2 pi is left over. So we have negative 1/3 r cubed, and then the integral going from 0 to 2 pi. And then, like I said, the antiderivative of sine of phi is going to be negative cosine of phi. And the limits of integration there are going to be 0 to pi. And we already dealt with the d phi, so that part just goes away. We're left with just d theta. All right. So now let's just deal with this part real quick. It's just some simple trigonometry. So cosine of pi is -1. Cosine of 0 is 1. So this works out to be negative 1/3 r cubed. And I'm going to move this whole thing outside of the integral because we've already integrated that part. There's nothing else to be done besides just plugging in the endpoints. So like I said, cosine of pi is negative 1. Cosine of 0 is 1. And then we have the integral from 0 to 2 pi of just d theta. So let's simplify things a little bit. So this right here is just negative 2. So we have negative 2. That's going to make it a positive 2 r cubed over 3. And then we have the integral 0 to 2 pi of d theta. So just like how the antiderivative of dx is x, the antiderivative of d theta is just going to be theta. So we have 2 times the radius cubed over 3. And then we have theta as the antiderivative going from 0 to 2 pi. So then we're going to have 2r cubed over 3. And then we have the top endpoint plugged in minus the bottom endpoint plugged in. So if we simplify, we get 4 pi r cubed over 3. So pretty exciting stuff. If you ever wondered where the volume of a sphere comes from, it comes from a 3D integral. It came from doing a multiple integral of a vector function across 3 spherical dimensions. We have a rho, we have a phi, and we have a theta. All right, guys, hope you found this useful. No promises, but I'm thinking about maybe doing some more Calc 3 videos in the future. Maybe some linear algebra too, maybe some stats. We'll see. Hope you guys have a fantastic weekend, and I'll see you next time. Ciao.